We are now recording the lab. So today the plan is to just answer any questions you guys have about the finals and about the final review questions specifically. And then if you have other questions, if we run out of questions on the final and you have other questions on anything else, I'm happy to talk about those too. So yeah, let's start with questions on the final exam review. If you guys have any questions about that, anything that wasn't clear, anything you'd like me to, any questions you'd like me to go over, I'm happy to do that. For the true, false, or justify, if the statement, you do want to look for statements that are slightly false. And when a statement is false, you only get half the points for recognizing that it's false, and the other half of the points are for actually pointing out what the falsehood is. And there might be a few different ways to edit the statement to make it true, and whichever way you choose is fine. As long as you don't just like cancel out the entire statement and like write a true statement instead of it, just you write a true statement about some of the information in the false statement, and that should be fine. Yeah, if any of these are confusing to you guys, if you want to go through
Just one
them,
thing I'm going to
edit
look up
them.
now, and I can't remember it there. I know that IANA isn't, or at least I mean, it's not. They're not the ones who are managing MAC addresses. There, I know that there is some organization that does determine like MAC assignment to companies. Do you know what that is, or?
I don't actually know what that is. Yeah, I
Let me
only
see
know
if I
kind
can
of.
pull that up. Just to remind me.
Yeah. Did Gabe mention that at any point in the class?
I don't think so. It's just something that I know I've looked up before. So to do device IDing.
Got it. So for anybody else in the lab right now, if you're looking at that question, like Pierre mentioned, it's IANA is not the authority that delegates MAC addresses. So for you, from the class, you know what IANA is, and so the way that you would edit this statement is by just saying what IANA actually is.
Regarding BGP, I remember whenever we talked about it in class in terms of choosing routes, like the properties in which we were looking for, Gabe kind of mentioned that it was not random, but like it kind of depends. It's not like some generic way that BGP chooses its path. So for
Right.
does that mean there is no like textbook decision? It's really just dependent on like.
So different implementations of BGPs will differ, but when he says a textbook BGP, he's talking about the kind of basic implementation of BGP, which is how you would expect BGP implementations to be.
Okay.
And there is kind of a general guideline for what your BGP implementation should look like. So there are some things that you can kind of choose on your own, but generally you do want to do this longest subprefix match, and then you want to do the shortest AS path once you've done the subprefix matching.
Okay, and then I don't get for 3 for true or false. What does it mean in looking at the relative specificity of the routes? Like,
so it says textbook BGP decisions choose between competing routes, first by considering the length of the AS path of the route, and then looking at the relative specificity of the routes. The relative specificity of the routes is this subprefix, the longest subprefix match. So if you have a route that is, so you want to get to 3.1.13, and one party has claimed 3.1 with everything else kind of left open, so that AS has access to all of those IP addresses. But you see another AS that says, I actually have access to all the IP addresses that are 3.1.1 with the last few bits left open, then you'd actually route to the more specific one. So you'd route to the one that has more of a match, has more of the bits kind of fixed the same as your IP address.
that makes sense. Thank you.
Yeah. And you actually do that even if the AS path is longer. that's why that's the first attack that gets protected against. So the RPKI protects against that, and then later in our timeline we are trying to figure out how to protect against more, right? But the first
Yes,
thing that
that
we
would be
protect
something to
against,
correct in that question.
what would be something to correct in this question?
Because they say first consider the AS path and then look at the relative specificity. Weren't you saying that?
Yep. Yeah, you're absolutely correct. So this would be false, but not because either of the checks are wrong, but just because they're stated in the wrong order. The AS path is the second order. Like that's what you would check once you've figured out your subprefix matching.
Actually, so going through some of the other things here. So with the DNS question, for example, at least what comes to mind for me was from like a server administrator role, making sure to prevent the abuse of the DNS server for reflection attacks. Were there other directions with the DNS protocol that were being considered as like possible answers? I mean, because DNS has its own issues, but was just sort of curious if there are other ones that came to mind.
The main thing that I believe Gabe's looking for with this question is the kind of iterative resolving versus recursive resolving. So basically, if you mention, hey, you're setting up a DNS server, make sure to do iterative resolving to prevent cache poisoning, and then to make sure that you're checking these things to prevent reflection attacks, maybe. I think you're totally fine. That's a perfectly good
Gotcha.
answer.
Yeah,
And
yeah,
I think,
and the
yeah.
recursive resolving as something that allows people to shortcut it and use that as an attack vector.
Right. And the reason why that becomes an attack vector is you can basically do DNS cache poisoning, right? And then the DNS server will kind of have this faulty resolution for an address already cached, and it will send it to people, and that will be wrong. And then the other thing that you can do with the recursive resolving, I believe, is basically just a denial of service attack. I don't remember the exact details of that, but basically recursive resolving is just more vulnerable than iterative resolving. So just remembering that and remembering the differences between them. Problem 4 is an interesting problem. So problem 4 says, you have a new hire that joins your engineering team at Super Secure Protocol LLC, who hasn't had the pleasure of taking a network security course. They've been handed off a draft version of the protocol that they're supposed to implement, and the draft states all message in the system should be encrypted and have their source and destination authenticated. Unfortunately, the designers didn't give any more details about encryption and how encryption and signatures should be composed to get this property. What would you tell the new hire to do? So here, basically, you want to think about how, the biggest thing here is kind of decoding this scenario into what you would have to think about theoretically from the course. So it's about kind of applying the things that we learned in the course to really figure out what the question is asking. And it's a real life scenario that you might very well be in, right? If somebody knows that you've taken this network security course, they might come up to you at work and just say, hey, I was just wondering about this thing. Do you know the answer to it? And the answer that you're looking for here is basically how sign then encrypt should be composed. Should you sign and then encrypt, or should you encrypt and then sign? And another question that's very similar to this, that's not asked on this final exam review, that was covered at the same time or pretty close to then, is the MAC then encrypt question of, should you MAC then encrypt or should you encrypt then MAC? And then the difference between what sign then encrypt is what signatures protect and what MACs protect. Because MACs essentially give you data authenticity and signatures give you identity authenticity. So that's the question that's happening there, problem 4. Consider TLS 1.2 using strong symmetric key ciphers and key encapsulation. Does this protocol offer post-compromise security against an adversary that compromises the server? So here you'd have to understand the definition of post-compromise security and remember what TLS 1.2 does. So what the function of TLS is, what would compromising the server, what information would that give you, and what would this post-compromise security be of? If you're unsure of any of these things, you can ask clarifying questions.
Yeah,
But as
actually, on
long as you
that,
kind of state your assumptions, you're fine. Yeah, tell me.
yeah. So on that topic, so if I'm remembering correctly, you do have the option of using ephemeral Diffie-Hellman in TLS 1.2. I think it's one of the many ways in which you could use that. And so, say selecting that approach rather than using something like key encapsulation or static Diffie-Hellman would provide different guarantees. Would you want, or would that be something where you'd say maybe propose both of them and describe how one might have some features versus the other, or just pick one and talk about it?
I think that your answer makes sense. So if you kind of stated that, if the person's using key encapsulation, then really once the server is compromised, every other time you're going to be able to kind of eavesdrop on that conversation. But if you have ephemeral Diffie-Hellman, then the server is picking a new key every time. So actually, once the adversary leaves, you're gonna get healing again, where the attacker can't compromise the new conversations that the server is having. Then, like, that's a very good answer.
Okay. Okay, sounds good.
Yeah. So let's see. Problem 8. Right. So this one is just saying if you have a public encryption scheme and a symmetric encryption scheme, how do you get hybrid encryption? And this is something that was covered in class. So this is more of a recall question. And then what is the benefit of using such a scheme instead of just using public key encryption scheme alone? So if you remember this, this will be really quick. If you don't remember it, it'll, finding it will probably be hard and take away time from the other questions. So that's kind of what I mean by you don't have to memorize anything, but this is kind of an intuitive thing where if you understood the lectures and you were following the class, you probably remember this. The I won't kind of say the answer here just because I think it's good for you guys to review and be able to kind of do the problem set yourself and figure out, how you feel about it, how good you feel about how quickly you were able to solve it. Problem 9 is kind of, I think, was covered right in the beginning of class. We had BGP, and then we have RPKI, and then we have BGP-SEC, which are these 3 levels of security. So as long as you remember what BGP is and how it works, and then you remember RPKIs and ROAs, then you should be able to answer this question. I had a question in the previous lab asking kind of the format of BGP messages, announcements. So if that's a thing that any of you were wondering about, I can show you kind of an example. So here's an example. And basically, this is an announcement. And basically, NTT is announcing that if you go through me, then I have this AS path to this IP address. So if you want to get to a sub prefix of this IP address, then if you send me the message, I'll send it to NLayer, who'll send it to SCNet, who'll send it to 2997. BGP is the protocol that's supposed to help the different autonomous systems route messages between themselves. So these autonomous systems kind of are physically connected in some sense, right? And you want to route messages between them, but you don't know this graph beforehand. So you can't just draw the graph and say, oh, if a message has to go here, then obviously you send it through this person and this person and this person. It's something that's kind of happening ad hoc as we speak, and it kind of built up over time. So we needed a protocol that could deal with that. And so the way that BGP routing works is that you announce, as an autonomous system, you say, here are the IP addresses that I've been allotted by IANA or by the authority in my particular region. And so these are the IP addresses I've been allotted. Here's my ASID. And you just announce that to all of the autonomous systems you're connected to. And then all of the autonomous systems you're connected to send out a message saying, we're connected to this autonomous system who was allotted these IP addresses, and we can route messages to them. And so that's what's happening here. So at this layer, this is just 2997 saying, I'm 2997, here's my IP address. Here's a set of IP addresses that were allotted to me. Then you have SCNet saying, I'm SCNet, my path to 2997, to go to these IP prefixes is one long, right? So you can kind of get to 2997 just directly through me. This path is just one edge long. So basically giving the path and giving kind of the IP addresses that path goes to. And same thing happens at the third layer, and layer says, I have a path to these IP addresses. It goes through SCNet and it goes through 2997. So my path is 2 edges long to these IP addresses, and so on and so forth. So that's what's happening in the BGP announcements. And then what happens when you get a message is your, say, NTT gets a message saying, I need to go to 204.16.254.13, right? So that's a sub prefix of this IP address. Also, this is something, I don't know if you remember, but just to reload, for IP addresses, when you have a /24, it means that the last 24 bits are fixed, or the first 24 bits are fixed. I believe, but I will check that just in case. It's right here. Yep, /24 means the first 24 bits are fixed. And each address is 32 bits, so that gives you how many free bits there will be. So if you have a /8, you have way, way more IP addresses than if you have a /24. And so that's what people are referring to when they talk about sub prefixes. Because when they talk about a sub prefix, say that one person, forget people actually. So say that you have this IP address. Right? Then what you can say is that the IP address that looks like this is a sub prefix. So maybe I should write sub prefix next to the one that's a sub prefix instead of in the middle. So that's useful to just, it's a term that's useful to remember for when you're learning about sub prefix hijacking and when you're learning about shortest AS paths. These are the AS paths, and these are kind of their lengths, is how many autonomous systems you have to go through to get to the autonomous system you're trying to get to. And then this is what a prefix is, this is what a sub prefix is, and this is how we talk about them. So now BGP is called a path vector protocol. Each network just puts its name on the path. This is not a thing we learned in this class, but if it's useful to you, it helped me kind of, the more information you have, the more you can remember like the details that the higher level details when you know some lower level details. So let's see, what are the two main things that happens in BGP? Like just base BGP without RPKI, we have two properties. We have longest prefix match routing, where we're gonna route regardless of how far away this autonomous system is. If they have more of a match of their fixed bits to this IP address, then we're gonna route to them. So if, for example, we knew an autonomous system that announced this, and we knew an autonomous system that announced this, and we saw an IP address 204.16.254.13, we would actually send it here, even if the AS path was way, way longer than the AS path to this one. And that's a thing that happens in BGP. It's a thing to remember. The idea is you want to send it to like the autonomous system that actually has that IP address in their ecosystem. Okay, so there's that. And then the other part of this is that you're gonna, once you have those subprefix matches, say you have two different people that have announced this one, and you know you have to route a message to one of the autonomous systems that's announced this guy, then you're gonna look for the shortest AS path. So once you've done the longest subprefix match, then you'll do the shortest AS path, and that is base BGP. The first level on top of that is RPKI. RPKI is just ROAs, if you remember ROAs. They basically are kind of certificates. They're not certificates in the sense that we learned before. They're actually just root origin authorizations, which means that, for example, when 2997 announces this, there should be a ROA that's up that says 2997 has been allotted these IP addresses. And so you are authorizing 2997 as the origin for the route that goes to these IP addresses. And so that's the ROA. And what RPKI does is whenever you get an announcement, you check the ending AS system, dot ending autonomous system, and you check the IP address that they've announced, and you make sure that there's a ROA out for that. And as long as there's a ROA out for that, then you accept it as truth. You say, okay, so this path must be correct. The thing that this prevents is what is called a subprefix hijack. A subprefix hijack is when you want to steal the traffic away from an autonomous system, and so you announce a sub prefix of what they've been allotted. But if you try to announce the sub prefix, you will not actually have the authorization to announce this sub prefix, because you will not have been allotted the sub prefix because you're an attacker. So there won't be a ROA for it. So you're not going to be able to do the sub prefix hijacking. You're still going to be able to do the shortest AS path hijacking if you have a shorter path, and you say, say that here, there's a path that is this long to go to 204.16.254.40, right? And this is something that actually happened. And Cyberbunker says, actually, I can get there in, wait, was this a subprefix hijack? This might have been a subprefix hijack. This was a subprefix hijack. But Cyberbunker, instead of saying just doing a subprefix hijack, could say I can get to 2997 in one hop, and I have the subprefix that 2997 has. Then anytime Greenhost wanted to send a message to this IP address, it would actually send it to Cyberbunker instead, because it had the shorter AS path, and they both had kind of announced the same end point of like the autonomous system and IP address combination. So that would be the kind of shortest AS path hijack. This is actually an example of a subprefix hijack that was actually carried out in the wild. So a ROA links an autonomous system to the IP prefixes allocated to it, and then the ROA itself is signed by the network operator who handed out the IP prefixes, but the ROA itself doesn't have any public keys linked to it, because we're not actually kind of using the ROAs to sign anything. The ROAs are just going to be a check. So you're going to go check when you see an announcement that the kind of final IP, the IP prefix matches the autonomous system that is linked to it. So if you were trying to announce a shorter path to 3.1.0.0/24, the way that you would do it is you would say, I am AS8, and then I am directly connected to AS7, and I want to announce 3.1.0.0/24. If you have a shorter path attack with the same path length as the real AS, would it still count as an attack? Right. So if you kind of, well, so the thing with the shortest path attack is it depends on where the message is coming from. So right now we're just thinking about one message, right? And so we can kind of think about whether that message actually gets intercepted. But if we're kind of thinking about just you announcing a shorter path to AS, say like 3.1.0.0, like to AS7 from kind of anywhere in the internet, then you would successfully hijack some of the messages, right? Because for some of the messages that are being sent to that IP address, you'd probably have a shorter AS path, but for some of them you wouldn't. So for the ones where the path length is the same as the real AS, you can't really be sure if the message will get routed through you or through the real path. But for ARPs, I would say you should probably go through these notes that so this is for my lecture 3 notes. And if you go down to here, I remind you how the link layer works. And if you watch it in tandem with Gabe's lecture, then the notes should match up kind of in structure to what Gabe's talking about, but sometimes they have more information a little bit, or they have information the way that I assimilated it. Not all my notes are super detailed, only some of them are, but ARP is pretty detailed. And so this is kind of how ARP works. And I think my ARP notes are pretty detailed. So once you read this, if you still have questions about how ARP works, definitely send me those questions on Piazza and I'll send you more detailed responses, just so that we have more time to get to the other questions about the final today.
Yeah, actually, that question does raise something. So as far as different, I guess, proofs or yeah, I guess security proofs are the best thing. So in dollar CPA, in dollar CCA, are there other particular ones that I mean, I haven't gone through and looked to it, but are there other particular ones that might be good to have on that list to review?
So essentially, I would kind of go through, now that you've seen the entire class, look at the crypto review sheet, and I can go through it and see, maybe post on Piazza what important definitions might be for you to understand. But really, in terms of the stuff that we covered in the class, like we're not going to test the crypto review because that's not what we covered in class. What you want to review for what we covered in class is, for example, the Diffie-Hellman key exchange. You want to really make sure you understand Diffie-Hellman key exchange, how the two parties, why the keys are secure, what the public half is doing, what the private half is doing, how you're encrypting messages under it. So if you're having issues with why something is secure encryption and what it means for something to be secure encryption, that's when I'd go back and look at the definitions. But if you kind of understand that, the CPA security question is a little bit of a one-off because it's about this very specific definition. But the kind of content of it is to really figure out this, how to use this Diffie-Hellman key to get asymmetric encryption. And there you should have an idea of how somebody could do that once you understand how asymmetric encryption works. So I can actually just quickly tell you right now in the lab what this asymmetric encryption is supposed to be. So CPA secure essentially just means that if the attacker chooses two plain texts and the security game just chooses randomly between those two plain texts and encrypts one of them, and then the attacker has to guess which plain text was encrypted, that the attacker is only going to be able to guess the correct plain text about half the time. So they're not going to be able to get any advantage over just random guessing. And the reason why they're not going to be able to get any advantage over random guessing is because basically you want to say that there's nothing they could do to really learn anything about which message was encrypted. And you're given here a CPA secure encryption scheme that's symmetric. So as long as both people have the same key, this encryption scheme is going to satisfy CPA security. So the only thing you're left with now is to satisfy this asymmetry property. And the asymmetry property is that I, as the receiver, will publish a public key that everybody can see, and I will have some private key that I will keep to myself. And the sender is going to use my public key to encrypt a message to me that um, basically is hidden from everybody else. I can read that message because I can figure out how to decrypt it because of the private key that I'm holding, but nobody else can figure it out. And so this is where you're going to want to use your Diffie-Hellman key exchange, right? Because you know when somebody has a public value that they've sent you with a private value that they're storing for themselves, how you can send them a public message and share a secret key with them. And then, given that you already have this CPA secure encryption scheme, you can just use that key to get your asymmetric encryption to go through. And so this is what CPA security is, and you're going to be trying to get this security, but in the asymmetric case. So you're going to have a key K generated according to the algorithm gen, and then the adversary gives you any two messages, and what the game is going to do is going to encrypt one of these messages chosen uniformly according to the key that was generated according to the algorithm gen, and then the adversary will have to guess which message was hidden. And one of the things you want to make sure to do here in the asymmetric case when you're trying to get CPA security is you want to change your key, or I mean, you want to basically share a key, right? You have this public key. You don't just want to sign under that public key of the party that you're communicating with. You want to generate something on your part that will allow you to share a public key with that other party. Does that make sense? You're trying to get the same security as the CPA secure game, and you have a CPA secure symmetric encryption scheme, right? So you already know that you have an encryption and decryption scheme that satisfies the security as long as the key is hidden. So what you're left to do is find a way to share a hidden key with this party who's published their public key in a way where they don't have to communicate with you. They've already shared this public key and you just have to kind of communicate with them and you'll be fine. So can either of you think about how to do that, how to share a public key with the other party? So imagine this. Let's just start a new note. So imagine that you have this public figure or like this public, I don't know, server that you want to talk to that has a key G to the power of A. That's their public key, A is their private key, and they kind of announce G to the power of A. So they kind of announce that, right? So now you know G to the power of A, right? So the server says g to the power a, and you send back g to the power b. That's exactly correct. So the server will send g to the power a out, they announce it, and then your gen algorithm is, these are the algorithms you're going to write, is gen, encrypt, and decrypt. So your gen algorithm will just output b and g to the power of b. Your encrypt algorithm, which takes a public key and a message and outputs a ciphertext, will take, so we're going to do encrypt of g to the power of a, comma, message goes to symmetric encrypt of g to the power of a to the power of b, comma, message, comma, this g to the power of b. Does this make sense why this would be the encrypt algorithm? Because this, when you send them this, they can use their secret part, which is A, to compute this key, and then they can decrypt the message. So what is the decrypt algorithm going to look like? It's just going to be, so decrypt of some kind of ciphertext with g to the power of b, or let's call this c prime since this whole thing is called c, or right, and you have to give it your secret key. So you give it a secret key, which is going to be A, and then the message that it got is going to be this kind of encryption, the symmetric encryption of stuff, and g to the power of b. And what the decryption algorithm is going to do is it's going to take the symmetric decrypt function and just use it. So it's going to do symmetric decrypt of, now g to the power of b, which you had, raise it to the power of a, and then put in your symanc of stuff that you sent it here. This is just gonna, to them, just look like a ciphertext C. So PK can be sent in the clear. Yeah, PK can be sent in the clear. So always when you have asymmetric protocols, especially this asymmetric encryption, I'm going to be a party that shares a public key and I have a secret key. And basically what you want is to write an encryption scheme so that other people can use my public key to encrypt messages to me and nobody else can decrypt them aside from me. So you're able to kind of look at these like publicly available public keys and send messages to the party who announced these keys that will only be decryptable by the party that announced the key because they had this private part of the key. Shouldn't it be B instead of A and decrypt? So actually it shouldn't. The way this might be confusing. So maybe we write A, G to the power of A here. The gen algorithm for public key crypto or for asymmetric crypto is the gen algorithm for the party that's going to announce their message. So I, as a party who wants to do a public key encryption with, anybody who wants to send me messages, I'll use this gen algorithm. B is kind of a placeholder, right? It kind of, the gen algorithm picks an exponent, we can even call it X, and sends and gives you X and it gives you G to the power of X. Now the encrypt function, what it does is it picks this exponent B, it runs symanc on this Diffie-Hellman key that would be generated if you use B to get G to the power of AB. So you use G to the power of AB as the key and you encrypt this message under that. And then you send G to the power of B to this person who started the symmetric encryption protocol, who announced their Diffie-Hellman half. And then for, oh, I shouldn't have deleted B. So, and then for the decrypt function, the decrypt function will get this whole thing here. This thing will be the ciphertext for the decrypt function. And so the decrypt function needs some way of taking G to the power of B and getting the shared key. And the only way to do that for asymmetric encryption protocol is to use the secret key, which is going to be this value A. And so that's why you need A here within the decrypt function. Yeah, so this is basically going to be one side of the encryption in some sense, basically because what you're saying is this is a general encryption protocol where the gen and the decrypt refer to the party that is kind of announcing their key. And then the encrypt protocol refers to the party who is sending messages secretly to the party that, so the receiver uses gen and decrypt, and the sender uses encrypt. So the sender is also generating this Diffie-Hellman private public key pair, but their kind of their generation is not called a gen algorithm. It's all part of the encrypt algorithm. Because basically the public private key pair for this encryption algorithm is the one that the gen algorithm outputs, because every single party that communicates with the receiver will use the pair that the receiver announces, but every single party that communicates with the receiver will use a different pair to encrypt their own message, right? They'll choose a new exponent, etc., over here in within their encrypt algorithm.
So in this problem, you mentioned asynchronicity a couple times. Is that like expected to be a part of the answer? I know because Signal goes through a lot of we can receive messages asynchronously, but I don't, unless I'm missing it, I don't actually see in the
There's no asynchronicity. The main thing that is similar about the two cases is the fact that you can kind of the idea that you can take this symmetric encryption and decryption function that you have and use it as long as you can share these keys somehow.
Okay, got it. So we wouldn't be expected to include things like message number, length of what I just sent, length of previous messages sent, or other things that like Signal includes to help guarantee that we can achieve asynchronicity.
No, yeah, you wouldn't be expected to have any of that. So keygen will have a private key and a secret key. That's what you will define as what the private key looks like, what the secret key looks like. Encrypt will take that private key that you already defined before, a message that's just a plain text message that you want to send, and get a ciphertext for that message. And all you want is that when that party gets that ciphertext, which could include kind of additional data about other things, that they can get that message back from it. As long as they're able to get the message using your decrypt function. So the decrypt function should take just my secret key. So whatever you defined as my secret key in keygen, and whatever you defined as the ciphertext and encrypt, and be able to use just that information to compute the message. And as long as your decrypt function can do that, you're good. There are no message numbers. There's none of the, I mean, we're not going to expect you to come up with a different version of Signal. If you can work out problem 10 and really write out an answer to it, then you're more than good for the crypto part of it. And kind of figure out some of the definitions. Yeah. And I believe you're going to have access to your notes. So, you're going to have access to my notes as well. If you wanted, if you were just missing a definition, that's not going to be a problem. You can just go look at the definition. The problem is if you really need to look up a lot of things, because the exam's going to be kind of long for the time period that we're going to give you. just to make sure that you're mostly recalling information and not kind of spending the whole time looking things up. And if you've attended class, that will help. I think the true or false questions especially is one place where if you've attended class, that's very helpful. So let's see. What does problem 11 say? Imagine you have a 2 out of 3 threshold secret sharing scheme for which you share 345. Did you guys, oh, you guys covered secret sharing recently, right?
Yeah, we've been looking at that the last 2 or 3 classes.
Yeah, that's I think this question will be a good way to assimilate what's going on in secret sharing if you've kind of wanted just a concrete example to work out. This is just an example. You just have to do the interpolation. So you have your share, which is 345, and then the other party share is 573. So now you have the 2 shares that you need to figure out the y-intercept, and you just kind of figure out what line would go through these 2 points and find the y-intercept. And so it'll be a good way for you to remind yourself of the formulas and make sure that you can do the calculation. Problem 11 definitely work out because you've just learned secret sharing, and I think this is one of the first like concrete examples you have of the actual interpolation. But it's simple math. You just want to remind yourself that you can do the simple math, right? You have 2 points on a line. Can I kind of use that to get the y-intercept of the line? Is there anything else that you guys are a little bit unsure of, or kind of
Sorry. This is more of a like opinion question. What do you think we should spend the most time on understanding other than signal?
So honestly, I don't even necessarily think that signal is the thing that you should spend the most time on. The thing that I would do is for the first few topics in class, hopefully between the kind of notes that I posted and the terms that we posted that you should know the meanings of and the recordings of lectures, you should be able to just kind of review that stuff quickly, right? You should be able to look at the term list and then from that read the notes and just watch the lectures for any specifics that you don't remember, right? And then for the later on stuff, I would make sure that you understand the basic concept, right? So for example, if you were studying BGP, right, even for the earlier stuff, if you understand BGP, the protocol, and you understand RPKI, and you have an idea of how BGP-SEC works, you don't really you couldn't fully specify it, but you have an idea of how it works. That's a good level of detail to go into at the point where you should be like, I should maybe spend time on other things instead of making sure I absolutely understand every detail of this one protocol. The thing I will tell you is that there's going to be a lot of questions on this final, and I think Gabe is making a very like concerted effort to make sure that there are questions from all different parts of the class. And so that also means that everybody else in the class is answering questions from all different parts of the class. And everybody else in the class is answering a ton of questions. So what you want to do is make sure you know the material well enough that you can kind of recall these things quickly and figure out, if you forget the difference between, or you forget the order between the AS path route and the relative specificity of the routes, and you quickly go look that up in the lecture notes during the final, but everything else you pretty much remember, that's not going to hurt you so much. But if you have to do that for every single question, that'll hurt you. So once you fully conceptually understand a topic, you don't have to worry about mugging it up. But if you don't conceptually understand something, you're not going to be able to figure it out during the final because it's going to be too long to figure these things out during the final.
If no one else is going to ask, can I ask a question about signal?
Yeah, go for it.
Okay, so for problem 2C,
okay.
I posted about this on Piazza. Thank you for your answer. I think I actually finally managed to understand the question, which took me like 2 days, but whatever, no big deal. That's okay. Anyways, so I guess one of the things I'm starting to think is that the fact that we're using the same chain key twice as input to the KDFCK instead of just the chain key and a constant
Mhm.
doesn't really matter from a security standpoint, because isn't it true that as long as at least one of the inputs to a KDF function is random, then the output will appear random, and so then it doesn't really. I don't think we lose randomness by having the same input twice. Um,
Yeah.
Okay, so
Most of the difficulty of that question was understanding that question.
okay,
So
okay,
that's
all right,
that's exactly what it should, like, most of the questions that we have on that problem set, if you can really understand what the question is
yeah,
asking, it shouldn't be too difficult. Like, the obvious answer is the answer once you've understood all the different pieces and understand what the question's asking. um for that question, I will say, like, we on purpose didn't actually make this break, but one of the things that could happen is that you have the, say we were putting the root key in as input instead of putting the chain key in as input instead of the constant, you might end up in a situation where the parties aren't able to go forward in the chain and keep computing keys because they don't have the root key value that needs to be entered. Or, you might worry about breaking this immediate decryption property, because in the symmetric chain, you really want, the reason we have this constant is so that the parties can just compute all the keys for that epoch once they have the symmetric chain key. By inputting the chain key itself into both of the different inputs for the KDF, we don't really lose anything because you're always going to have the chain key because you needed to input it anyway. So you're fine. Yeah.
okay, great.
Yeah,
Thank you. One other question.
definitely. Mhm.
When an attacker, for part B, if an attacker were to compromise a device, is it fair to say that the attacker can learn the secret values X and Y? I know that the
If
problem statement says that the attacker can't learn X or Y from eavesdropping and seeing the values G to the X and G to the Y. But if a device is compromised, then the attacker can learn X and Y, right? Yeah.
Right.
Okay.
That's exactly what the compromise means, is that anything that you're storing in your local state in your device just becomes visible to the attacker. So anything that you can compute becomes something that the attacker can compute, right? Because when
Wait.
your device is compromised, you're
Mhm.
assuming that the attacker has kind of learned everything that you know in this moment. Yeah. Yes, Julie?
So at one compromise, Mallard can learn X and Y, not just one.
Mallory can learn whatever information you have stored on your device and can compute whatever you can compute. So if you have X stored on your device, Mallory can learn X. If you have
Mhm.
Y stored on your device, Mallory can learn Y. It just depends on,
Okay, that
you
changes my
can't
answer.
learn everything that was on everybody's device, because think about it
Right.
as a real world scenario, right? Like, think about it as a full state compromise as somebody who just got complete access to your phone. They broke into your phone, right? Now they know every single thing that the Signal app is doing to make your computations. They have access to the code and everything that's kind of, which means it has access to your chain keys that you've computed. It has access to the root key that you computed. It has access to, your long-term key. It has access to your secret half of your long-term key, all of it.
Cool. All right. Thank you.
So to follow up on that, the problem statement says that when Signal is installed on the person's phone, X and Y are fixed. So I took that to mean that, like, they're included in the app image, if you will, and hence both of them would be learnable if an attacker is able to compromise the device.
Which
Um,
question is this, or is this
also for 2B.
for 2B, let me just look at the question really quick so I can remind myself what's happening. Oh, right. So these are this is the rotating values. Right. So here, one thing is that only Alice's device has this buggy implementation. But
Right.
yes, once you break into Alice's device, you learn both X and Y at once, because it's something that the app is going to compute on download, and then it's just going to store these values, right?
Yeah. Okay. Because yeah. Okay.
That's
so
how
it's
it can cycle between the values, is that it's stored. Yeah.
Right.
The thing you want to think about is there going to be post-compromise security? When will there be post-compromise security? When will there not be post-compromise security? The idea is to make sure that you understand both the specification of signal and then the definitions of security that we're going for, and obviously what this post-state compromise means.